afternoon. I would like to introduce myself first. My name is Bea Astuti, and then in this opportunity I would like to present my proposed paper entitled Multi-Trajectory Prediction of Pedestrians based on Deep Neural Network Architecture. Okay, so the aims of our proposed paper is to design trajectory prediction algorithm. So to make the structural presentation, I would like to divide into four kind of the section. The first one is introduction, and then it would like to divide into two subsections, which is impact of trajectory prediction and the previous related benchmark. Okay, so now I would like to explain about the impact of pedestrian trajectory prediction. As we know, all of the car factories now have the ADAS system, or Advanced Driving Assistance System. What does that mean? They're using the pedestrian collision avoidance that leveraging the detection algorithm. So, but it has the disadvantage, which means that when the pedestrian moving suddenly in front of the car, it has no any sufficient time to make the system or the driver to brake the system itself. So we need the pedestrian trajectory prediction. So the impact itself is, the first one is the perception. What is perception? Means that the system or the autonomous or semi-autonomous driving car can recognize what kind of the object in front of the vehicles, and then after that when they detect the pedestrian itself, and it will predict where is the future of the location of the pedestrian, and after that, is that have any potential danger or no? If there is a potential danger, the system will make the planning and control whether it will brake the vehicles or no. And then the next one is, so there's lots of recent method or recent models that want to make sure the precise trajectory prediction. So I choose three models that have the recent one. So the first one is PI, which is pedestrian intention estimation. Second one is attention LSM, and the third one is GITP. So we can see they have the similar multimodal inputs. Or we can see multimodal learning inputs means that they inputs lots of information, whether it's image sequence, road context, and then after that they have object trajectory, ego vehicles, and so on. So here, but there's a disadvantage of inputting the multimodal learning inputs. What is that? It will increase the input network layers, and it will impact the overall total of the models, and it will impact also the trajectory prediction. And then this is the components of their proposed method. And then after that, all of them, these three related benchmarks, they predict only single trajectory. But we can know that human or the pedestrian itself, it has inherently uncertain nature, which means that they will have the changing the direction abruptly. When there's a car, they will move to the right or move to the left, and so on. So the single trajectory is untrustworthy. So now, to make sure that to cover this disadvantage, I would like to propose three kinds of contribution. So the first one is I would like to input the unimodal learning inputs, which called observe trajectory, their observation, to embed using the proposed temporal embedding. And then after that, instead just only considering the prediction of single trajectory, I would like to predict the multi-trajectory, and it will generate it through the attention mechanism. And then my proposed method, deep neural networks architecture, can achieve state-of-the-art, which is can have a better evaluation result rather than those three recent related works. So the next one, I would like to explain about the proposed method. First one, so here is the proposed method. The unimodal learning inputs, which is the observed trajectory, this one, the yellow one, is the observed trajectory sequences. So it will input as the observation period of time, and then it will input the trajectory embedding system, which consists of the fully connected layer. And in this fully connected layer have several networks, it will embed the input, which is become the embedding output system with the weight and the weight itself, and then after that it will input to the attention mechanism. It will resulting the embedding linear projections. It will input the multi-head attention, which have the attention mechanism itself with the help of the query, key, and the value, and the help with the softmax activation function to calculate the dot product of the Q and then also the key functions. It will input the ReLU and ReLU non-activation function and the normalization as part of the feedforward network, and then after that it will produce new embedding trajectory, which is producing the prediction of the current time of the pedestrian itself to the prediction horizon. It will input to the trajectory decoder, which the decoder itself, it will produce two kinds of trajectory prediction. The first one is single, and then the second one is the multi-predicted trajectory. So in here, the single predicted trajectory, single means just have one trajectory prediction. And then for multi-predicted trajectory, it has several kinds of trajectory prediction, and I choose 20 predicted trajectory with the help of Gaussian random factor to produce the variance or noise of the trajectory prediction. So to calculate the complexity and the convergence, whether my model can adapt well to the task, I focus to implement the mean squared error, which calculate from the observation until the prediction. So now I would like to explain about the experimental end result. So for the experimental itself, as the same as the related benchmark, I use JAD, which is Joint Attention and in Autonomous Driving, JAD, and also PI, Pedestrian Intention Estimation, which is proposed the PI models. And then the evaluation metric itself, I'm using the ADE, average displacement error. What is that means? It's calculate overall of the predicted trajectory from the current time and until the predicted horizon time. And then after that, there are final displacement error. Final displacement error means that to calculate the final or the goals of the pedestrian, where will they go? And then this is the parameters and training. And then the next one is, we can see that the proposed model, deep neural networks itself, can adapt well to the complexity and the convergence. We can see start from 15 episodes until 100 episodes, the MSE result is lower than 0.3, which means the closest with the 0, the better. Next one is the quantitative result, as same as the related benchmark, PI, JITP, and also attention LSTM. I input 0.5 second or 15 frames because they're using 30 frames per second of image sequence and predict 0.5 seconds. And then here, PI, they are using the traditional recurrent neural network. So basically, it has this advantage, which has the vanishing gradient. So in this attention LSTM, they focusing to take the advantage of LSTM because it can cover the drawback of the RNN networks to have to cover the vanishing gradient, but it has the disadvantage, which means it's more prone to overfitting. So they need the regulation techniques. So the regulation techniques itself, they implement the attention mechanism, and then this JITP, they are more focused solely at from the transformer network, which is the stack of attention mechanism. As you can see here, that for the PI dataset, the lower the better, that my algorithm for the single trajectory have really better outperformed rather than the related benchmark here. And then for the multi-trajectory, I predict 20 kind of the trajectory, and then after that it can have a better. Why the multi-trajectory can have better result rather than the single trajectory? It's all because the multi-trajectory will have most of the prediction, right? And then it will take the best to the closest with the ground truth. Okay, So that is for the pi, and then similar for JAD dataset. Our algorithm can outperform from the related benchmark. So here, okay, here is the qualitative result for the pi dataset. As we can see, for the single trajectory prediction, the yellow one is observer, red one prediction, green one is ground truth. The well or the better the ground truth and prediction, it means that the DNN model, the proposed method, have a better. So we can see that my prediction for the single trajectory is really close with the ground truth. So that's why my ADE and FDE is better for the single trajectory. And then we can see here that for the multi-trajectory prediction here, that we can see there's a loss of the plausible or possibility for the future trajectory for the person itself. We can see they have to the right side, left side, and etc. Yes?
For those figures, you have to stop. You have no choice because they are on the road.
Okay, I will.
So why do you need to predict the
Okay,
direction?
later I will show the video. Okay.
We don't have time.
Yeah, it's okay. This one is for JA. So this one is the video. Okay. We can see the single trajectory. This is the single trajectory, and then this is the multi-trajectory. So it will continuously when it's record, and after that it will just predict like this. This is for one of the result for the scenes, and that's all from me. This is for the conclusion. So unless instead the inputting the multimodal learning trajectory prediction, I more focused to exploit unimodal learning trajectory because the previous related benchmark didn't exploit well the multimodal learning trajectory and multimodal learning input. And then after that, in order to produce lighter input layer network. And then after that, we proposed the stacked attention mechanism to predict both single and multi-trajectory. And then after that, our proposed deep neural network architecture can achieve the state of the art or the recent benchmarks. That's all from me. Thank you so much for your attention.
Thank you for your presentation, and I'm sorry if we can't have the Q&A because it's